सो हेलो गाइस, ये जो वीडियो सीरीज़ रहेगी ये मटेरियल साइंस के पर्सपेक्टिव से रहेगी और इसके अंदर हम मटेरियल साइंस को बेसिक से एडवांस के लिए कवर करेंगे। ये मेरी लिटिल बिट इन्फॉर्मेशन है, आई विल नॉट रिवील हु आई एम, बट दिस इज सम ऑफ द क्रेडेंशियल दैट यू कैन यूज़, that I have cleared GATE 6 times in a row, PSU selected 3 times, PSU selected. Now coming to the point, what is material science from basic to advanced? And materials can be classified as alloys as well as compounds. This will be used particularly for the mechanical engineers who will be appearing in GATE or engineering services exam. Material science is the foundational subject for production engineering also. So you have to understand the material science from very basics and grasp the content, and if let me know through comments if you have any query or some doubts that are not resolved through this video content. Now coming to the alloys is A and B. Alloy is basically made up of two elements, A and B, and this is a mixture means like just like salt and water. Compound is A to B, like this is an independent entity. Two elements of A and one element of B combined to form this compound. It is like H2O. So this is the basics about alloy. This will not come into the exam, but this is required. Now there is one rule. I will be slow and give pauses in between to let, if somebody wants to take down the notes, then it's fine. Otherwise I will be going with the pace. So alloys form when Hume, this is one scientist, Hume-Rothery rule satisfies. अब ये रूल क्या कहता है? अब ये रूल कहता है कि एक तो इसके अंदर जो एटॉमिक रेडियस है जो दोनों मटेरियल्स की है वो लेस देन 15% का डिफरेंस हो इन दोनों में। मतलब अगर मान लो कि एक की आर ए है एक की आर बी है, तो इन दोनों के बीच का डिफरेंस जो है 15% से कम हो। वैलेंसी जो है सेम हो। अब इसमें एक एक्सेप्शन है Fe3C, ये एक्सेप्शन है बट ठीक है। Electron negativity and electron affinity of both should be comparable. Electron negativity and affinity. और अगर alloys के अंदर होता क्या है कि ये जो मिक्सचर है जो कम्बिनेशन से बनता है, ये एक ऐसा कम्बिनेशन होता है कि जो कम्बिनेशन होता है वो किसी एक इंडिविजुअल की प्रॉपर्टी को रिफ्लेक्ट करता है। लेकिन अगर दोनों के दोनों लूज देयर इंडिविजुअलिटी देन इट्स कंपाउंड। तो ये बेसिक हमने पढ़ लिया अलॉयज के बारे में। नाउ कमिंग टू क्रिस्टल स्ट्रक्चर, ये एक इम्पोर्टेंट फैक्टर होता है और इसके अंदर अलॉयज की मैन्युफैक्चरिंग, अलॉयज की डेवलपमेंट के अंदर। एंड इलेक्ट्रॉन नेगेटिविटी जो होती है वो जो होती है इलेक्ट्रॉन नेगेटिविटी अगर किसी को नहीं समझ आता है तो टेंडेंसी टू अट्रैक्ट अदर इलेक्ट्रॉन्स एंड इलेक्ट्रॉन एफिनिटी इज टू अट्रैक्ट इट्स ओन इलेक्ट्रॉन्स। तो नेगेटिविटी मीन्स कि कितने कम, मतलब कितना नेगेटिव है, और इससे क्या होगा कि अदर्स के, और एफिनिटी में खुद के ओन इलेक्ट्रॉन्स को अट्रैक्ट करने की जो एबिलिटी होती है उसको इलेक्ट्रॉन नेगेटिविटी एंड इलेक्ट्रॉन एफिनिटी के अंदर से डिफाइन किया जाता है। और अगर लेट अस सपोज इफ एन एलिमेंट has more electron affinity, it means it will attract its own electrons more strongly, and then the size of the atom will be small. Alloy is stronger than the pure metal always, so this is one point. Alloy जो होता है वो stronger होता है प्योर मेटल से. लेट अस सपोज अगर तुम कॉपर का अलॉय बनाते हो तो इट विल बी मोर स्ट्रॉन्गर देन द कॉपर. और अब आ जाता है फेज डायग्राम्स. तो फेज डायग्राम्स इस वीडियो सीरीज के अंदर हम लोग PYQs एज वेल एज मॉक टेस्ट भी अपीयर करेंगे. तो फेज डायग्राम्स क्या होता है? फेज, अब देखो डायग्राम है तो इट विल बी सम प्लॉट. सो इट इज ए प्लॉट ऑन टेम्परेचर कंपोजिशन शोइंग द स्टेबिलिटी ऑफ वेरियस फेजेस. तो दिस इज द डेफिनेशन. ये क्या होगा? ये इधर टेम्परेचर आ जाएगा और कंपोजिशन के ऊपर एक प्लॉट है. अब ये प्लॉट क्या दिखाता है? इट इज ए प्लॉट ऑन टेम्परेचर एंड कंपोजिशन एक्सिस दैट शो स्टेबिलिटी ऑफ various phases. It means phase diagram just show the stability of various phases, but on temperature and composition. Means a phase can be stable at a certain temperature for a particular composition, but not be unstable at another temperature for the same composition. Also, we can say like if the phases are changing, so phase diagram give us the melting point of alloy at a particular composition. So if we fix the composition, for example this is the composition, then if we go, so it will give the melting point of alloy at a fixed composition. Now there is one rule, Gibbs phase rule, Cp plus F C plus 2. This is the rule. Now what is this P, what is this F, what is this C, what is this 2? So means phase, P is phase, F is degree of freedom, C is component, and 2 is 2. This is a numerical value, but 2 will become 1 if we reduce the degree of freedom. Like if we fix the pressure as atmospheric pressure, then this will be C plus 1. This is generally used because the phase diagrams are drawn at a particular pressure, that is atmospheric pressure. So now what is the definition of this phase? So how you define phase? So phase is physically distinct, chemically homogeneous, mechanically separable. So physically distinct, chemically homogeneous, mechanically separable. Component is either element or number of compounds, or degree of freedom is independent variables of property required to define state of material completely. You can go back and see again this video if you want to make down the notes. So degree of freedom means these are the number of independent variables of property required to define the state of the material. Like if you want to define a state, then how many independent variables are required? Physically distinct and chemically homogeneous, mechanically separable, we will be learning in further lectures, like how we will be defining the phases. So now the phases say, so microstructure is stable only when Gibbs phase rule is satisfied. And since in material science we will be only concerned with the microstructure, so we will be only focusing on the Gibbs phase rule. So we try to satisfy the Gibbs phase rule because we want to know which microstructure is stable. Now based on this, people have classified the phase diagrams. So first is, अगर क्लासिफिकेशन की बात करनी है, नंबर ऑफ कंपोनेंट्स. नंबर ऑफ कंपोनेंट्स के बेस के ऊपर यूनरी, बाइनरी, टर्नरी. सो इसमें कंपोनेंट 1, कंपोनेंट 2, कंपोनेंट 3 एंड सो. Now component 3. So unary phase diagram means component, if the component is 1, it means phase, it is pure substance. So one example is this, like T and P, and shown. So this is for graphite. So this is graphite, and at 3000 Kelvin at 125 bar it becomes diamond. C is equal to T means binary phase diagram, and C is equal to 3 is ternary phase diagram. So binary phase diagram is like T, here is percentage of A, percentage of B, and this is 0% B, this is 0% A, and in this direction the composition of B increases. Ternary phase diagram is like this. This is here percentage of A increases, here percentage of B increases, and here percentage of C increases. Now the second classification, binary phase diagrams. It is particularly for binary, and then it is classified. So first is type 1, 2, 3. So type 1 means isomorphism. Material that are completely soluble in the liquid as well as in the solid. So example is copper, nickel. So 100% nickel. For example, if you increase the composition of copper from 0% weight percent to 100 weight percent, then at any point in the composition you will not see that these are not mixed properly. So they are completely soluble. So completely soluble. Type 2 is material that are completely soluble in the liquid state but partially soluble in the solid state. So this is completely soluble, liquid or solid. In liquid, yes, they are completely soluble, but in solid they are not, they are partly soluble. So this is eutectic. Then the third, are those which are not soluble, neither in the liquid neither in the solid. So this is not in liquid, not in solid. So these are the phase diagrams, classification of the phase diagrams. So based on this people have classified. So now coming to first type, that is type 1. So now we will learn about type 1. So in type 1 what we have studied, it is completely soluble in liquid, completely soluble in solid. Example is copper, nickel. Now what you have to do, you have to draw this phase diagram. So first you will see copper and this is nickel. First make these 2 points. This is 1085 degree centigrade, this is 1452 degree centigrade. Then join these. This is liquidus, this is solidus, this is messy zone, this is copper, this is nickel, this is percentage of nickel. Now this is T max, this is T min. Now you say mass fraction of liquid, mass fraction of solid. So mass fraction of solid plus mass fraction of liquid is equal to 1. This will be happening in mushy zone where both solid and liquid both will be present. So then you say mass of solid into composition in solid plus mass in liquid composition in liquid is equal to optimum composition. So this is if you want to find the optimum composition of any element. So this is the formula. So now using these equation 1 and equation 2, if you want to find out, then like this is one variable, this is second variable. So if you want to find out ms is equal to C0 minus Cl Cs minus Cl. So this is solid liquid. So this is called as lever rule, and mass in liquid is equal to Cs minus C0, composition in the solid, and Cs minus Cl. So if you want to find, for example, if this is the case and you want to find this is C0, you want to find at this point, at this temperature, there will be some liquid, there will be some solid. You want to find what is the mass fraction, of the solid at this point of time. Then you say this as a fulcrum. Then you say this, if it would have been, this is liquid, this is solid, this is liquid plus solid. So you will say if the composition would have been this at this temperature, this will be completely liquid. So the liquid will be having this composition. So this is C liquid, and if it would be having this composition Cs, so then you will be able to find out how much will be the mass fraction. Now there are certain conditions which you have to remember. First, lever rule can be applied in binary phase diagram. This on phase diagram, if any line is there which separates the liquid zone, liquid phase with the mushy zone, it is called as liquidus, and on the phase diagram that separates mushy zone from the solid phase is called as solidus. And if two material combine together and produce a single phase in the solid state, it is called as solid solution or solutionizing. Mushy zone is the characteristic of the particular alloy. Larger is the extent of the mushy zone, lesser will be the fluidity of the liquid metal, and hence more variation will be there in the properties of that alloy. So these are the things that you have to remember. Like mushy zone is the characteristic of a particular alloy. What it means is that if particular alloy show particular kind of mushy zone, if the extent of the mushy zone is larger, then the fluidity of the liquid metal will be lesser. Now we have to understand what is grain boundary, how these grains develop, what happens to if we increase the cooling rate, and all these things. So now all these things we will be understanding using the phase diagram. So let us have this. So we have understood the lever rule. Also, if you wait 1 second, I can give you one more definition. I think I have some other location. This we have, like, in order to make you more clear about this concept of alloys as well as phase diagrams. So phase is defined as the homogeneous portion of the system which has uniform physical and chemical characteristics. And solid solution, it is composed of solvent and solute, and the one in more abundant is solvent, while in the less is called solute. Solid solubility limit is the maximum concentration of the solute atom which may dissolve in solvent to form a solid solution is called as solubility limit. And then it is completely like same. Okay, and I will also give you some more things from the Callister book, but right now I am not able to get this, but we will make some separate video onto that. First of all, let us clear all this which is available to us. Now what we do is we create this, because in phase you will have to you have to understand certain things which are not very easy, like there is a phase change from alpha to beta to gamma. So this is like crystal structure. If the crystal structure change, then also we say the phase change. So this is important. So this I wanted to tell you. I also wanted to give you the source reference, but this happens. It is not solid liquid phase, solid liquid gas. These are the phases that we have studied in 9th 10th classes. But in solids also, if the crystal structure changes, then also we say. Also from iron carbon diagram we will be learning about that at certain point the property changes, and then also we say that because there is a certain shift in the properties, then we say that there is a phase change or something like that. We will be studying it when it comes, but for the sake of simplicity I mentioned there. Now if you see, if we draw one line, and along this one line we want to find, this is A, this is A, this is B, this is C, this is D. So in A is completely liquid. B, there will be some liquid, this and this solid part will also be there. C will be, there will be solidification front. So this solidification front is there. Solidification front means the boundary between solid and liquid. This since this material is getting solidified, so this front is moving. So actually it is like a front which is moving. And if we see this, then we will observe that at core composition of nickel, let us suppose copper nickel, is 98%. However, at the surface it is different. So we will be explaining why this happens, how this happens. And then when these fuse in D, at D, when these fuse, these solidification front fuse, these act as grain boundaries. So this one arrangement is grain, and these boundaries are called as grain boundaries. And then there is a theta, which is a mismatch angle. Theta is equal to mismatch angle. So now based on this was done by some researcher, and he found out, and he said that if we cool from A to D, we can make some conclusions. If we decrease the temperature just by some units below the liquidus line to B, then we say that solid starts nucleating in microstructure at thousands of places. Upon slowly cooling the temperature from point B to C, we observed or the researcher observed by using the lever rule that as the temperature decreases, mass fraction of solid will increase. This is obvious. The moment solid nucleate at point B, percentage of nickel in the solid is quite high. But as the temperature decreases, percentage of nickel in solid decreases and approaches towards the overall composition C0. Because as the temperature decreases, the composition of liquid and solid will change. At high temperature, phenomena called diffusion appears in the material, in which material from high concentration diffuses toward the lower concentration. And as we cooling very slowly, there is a sufficient time for diffusion, so nickel diffuses from the center towards the outer direction, making the composition uniform throughout. It means if this is the solidification that is happening, at this point nickel will be higher in percentage, and at this the concentration is lower, so Fick's law will come into place and it will diffuse. And since the cooling rate is very slow, the time available will be sufficient enough to make the composition uniform throughout. And as the nucleus is growing, each solidification front will have a particular packing or orientation. So because when we decrease the temperature, solidification front will move, and each nucleus that appeared into the liquid at thousands of places will grow, and it will have packing and orientation, particular packing and orientation. And the moment the temperature of the sample slightly decreases below, like if this is the solidus line, slightly the temperature is below the solidus line, these solidification front will fuse together and the entire material converts into solid phase. The region where different solidification front are fusing, there will be a mismatch in the orientation of atoms. So if this is the region where this solidification front and this solidification front will fuse, there will be a mismatch in the orientation. So if this and so this mismatch is the mismatch angle, and this region of orientation mismatch are called as grain boundaries. Grain boundaries, atoms are said to be at high energy level, because every atom wants to decrease its energy, so they want to go to the minimum energy. But at these places the bond length is higher, so they are at high energy level, have more Gibbs free energy because have larger bond length. So Gibbs free energy, this is an important concept we will be covering in other courses. So Gibbs free energy will be higher, bond length will be higher, and bond can be broken easily. So if the bond can be broken easily, it is an easy attack site for foreign atoms. So foreign atoms will attack. It is an easy attack site for the foreign atoms. So foreign attack will attack, and corrosion will take place and starts at the grain boundary. And if the grain structure is more fine, fine means more number of grains, then the grain boundary will increase and the corrosion will take place faster. So the corrosion rate increases with the reduction in the grain size. Also, you might have heard about stainless steel. So to reduce the corrosion resistance, chromium is added. chromium after reacting with oxygen makes Cr2O3, and being the foreign material, it will be accumulated at the grain boundary, protecting the grain from the atmospheric gases. So if this was the grain, so at this location Cr2O3 will be chromium will come at the grain boundary, because this is a foreign atom and more space is available at the grain boundary, so foreign atom will be displaced on this side, so more, and oxygen try to attack, so it will form Cr2O3, and this is a protective layer, it stops further oxidation. Similarly, we can also add copper instead of chromium, but this is cheaper, so chromium is cheaper as compared to copper, and copper is expensive as compared to chromium. That's why chromium is more, but however copper has 4 times anti-corrosion properties. So anti-corrosion properties of copper are superior to chromium, but since economics comes into play, so chromium is followed. And what happens if we give no time for the diffusion? It means we cool the material from the liquid state to the solid state at a very fast rate. Then the diffusion will not take place, because there will not be sufficient time for the nickel atoms to diffuse from the high concentration zones at the core to the low concentration zones at the periphery. So there will be a concentration mismatch. Then comes like metal working. So metal working, cold working less than 0.4 Tm, warm working 0.4 to 0.6, and hot 0.6 से ज़्यादा. Tm, it is Tm, melting point. Lesser the percentage nickel, lesser is the melting point for the alloy. So it also depends upon the phase diagram. So if this is the phase diagram, and we know that copper has less melting point as compared to nickel, so if the composition of nickel is lower, then the melting point is also lower. So it means this cold working, warm working and hot working also depends upon this. Now what we have seen is that if we cool fast, then percentage of nickel will be higher at the core and lesser at the surface, and because of this the melting point will be different. And upon hot working, this core will remain solid because the melting point is higher, and the surface of these grains will become liquid. So along the grain boundaries there will be melting, and it will produce cracks which lead to brittle fracture, and this phenomena is called as coring or miscibility gap. So this is an important term. People ask this in interview as well as in certain competitive exams. What is coring? What is miscibility gap? Why it happens? And whether it happens because of the fast rate of cooling or slow rate of cooling. So these things you have to understand. Now we have discussed that there will be brittle fracture. So types of fracture we can discuss in small detail. So there are 2 types of fracture: brittle, ductile. So in brittle fracture, crack propagation, and this is a cleavage, and this is dimple will appear. Cup and cone fracture. Cup and cone fracture, this is intergranular, so it will happen along the, so intergranular, and this is intragranular. Then comes equicohesion temperature. Then comes equicohesion temperature. So at this temperature, strength of grain and grain boundary is same. Equicohesion, same. Equi means same, cohesion means between the same material. So cohesion between the strength of grain and grain boundary is same. And below this temperature, the material fails in brittle mode. Brittle mode. Now comes type 2. So we have discussed this is completely soluble in liquid, partly soluble in solid, and these are called as eutectic. Sorry, not equi, it is eutectic phase diagrams. Eutectic. So this word comes. These words will appear, and I will make one small video how these words comes and how they affect. So eutectic phase diagram. One example is lead and tin. So PBSN. So this is a solder alloy. So this will clear maximum concepts. This is the most important one. Mostly this is used because most of the alloys follow this. So what happens is this there is one notch, then this, and then there is one notch on this side. So this is alpha, this is beta, this is liquid. So in between you draw any horizontal line, in between it will be alpha plus liquid. Here liquid plus beta, this is beta, completely beta, and below this will be alpha plus beta. This is an important point, eutectic. If we write this point, this is 183 degree centigrade and 62% tin. This is 18%, this is 62%, this is 97%. Above is liquid, this is solid. Then there is one line, this is called as solvus. We will be discussing about this. Alpha is solid solution of, this is PB, this is SN, of SN in PB. Beta is solid solution of PB in SN. Maximum solid solubility will be there at 183 degree centigrade, and upon decreasing the temperature, solid solubility of material also decrease. So this is the maximum solid solubility. So 18% of tin can be absorbed in PB to make a homogeneous mixture. Above this, the solid solubility decreases. So if the temperature is below 183 degree centigrade, the solid solubility decreases of the material. Then comes 1-to-1 principle. So This is one-to-one principle. So what is one principle? In this, we draw a horizontal line on phase diagram, one end in one phase, another end in another phase. Then the space enclosed between the both is a mixture of two. So we have shown this on this slide. If we draw any horizontal line, one end on one phase, another end on another phase, then the space enclosed between the both is a mixture of two. Any line on the phase diagram that separate a single solid phase with a mixture of solid phases is called as, this is a single solid phase, mixture of solid phases. This is a mixture of solid phases. This is not single phase. This is a mixture of phases. This is solvers. Phase diagram where there is a partial solid solubility. There appears a point at which there is no mushy zone, and upon cooling liquid converts into two different solids. This point is called as eutectic point. So this is the definition of eutectic point. So eutectic point, what it says? It says it is only observed where type 2, where there is completely solubility in the liquid and partly soluble in the solid phase. There appears a point at which there is no mushy zone. At this point there is no mushy zone, and liquid directly converts into solids, and liquid directly convert into solid, but it will be two different solids. So eutectic is said to be, so one-to-one principle we have understood. If we draw any horizontal line which connects one end on one phase and another end on another phase, then the space enclosed in between is a mixture of two. Now eutectic, so liquid will convert into alpha plus beta. This is solid 1, this is solid 2. So now we have learned P plus F is equal to C plus 1, because generally plotted at a constant pressure. Now number of phases. If we put number of phases 3, because 2 solid phases and 1 liquid phase, so 3 plus F component will be 2 plus 1, so F is equal to 0. So this is called as invariant point. This is generally asked in the competitive exams, why eutectic point is the invariant point. And degree of freedom means it is fixed at particular temperature and composition. You cannot achieve eutectic at some other temperature and composition. And 3 phases are in equilibrium. 3 phases are in equilibrium. Now there are certain questions which are generally asked using lever rule, and now comes the type 3. Not soluble, that are completely soluble in liquid but are completely insoluble in solid. This is A plus B, liquid. This is liquid plus A, this is liquid plus B. Now in the upcoming video we will be learning about iron carbon system, which is a very important system, and iron carbon phase diagrams. This foam, steel, and all the engineering, mechanical engineering, this is the most important phase diagram, iron carbon phase diagram. So thank you, and we will cover in okay. So one thing I have forgot to mention, like I thought I have mentioned somewhere when I was mentioning about type 2 or type 3. So this is actually in this liquid, it is completely soluble in liquid, but not complete, it is completely insoluble in the solid phase. And if you find this, then this is the final thing, that it is completely soluble in liquid. I somehow misinterpreted it, and thank you.